Look up tonight. Find the north. Trace that familiar, unmistakable W scratched across the winter sky, the constellation Cassiopeiae. And find the star at its very centre. That is Gamma Cassiopeiae. You can see it without a telescope. You can point at it with your bare hand. And for over a century, it has been hiding one of the most perplexing secrets in all of stellar astrophysics. Why was it burning with X-rays no star of its type should ever produce? Where was the heat coming from? And what, exactly, was living in its shadow? The answer, when it finally arrived in the spring of 2026, rewrote the rulebook for an entire class of stars and opened a door we had not expected to find. There is something quietly extraordinary about a star you can see with the naked eye, that also happens to be one of the most studied and most debated stellar objects in the history of modern astronomy. Gamma Cassiopeiae, catalogued by astronomers as Gamma Cass, designated HD 5394, and given the traditional Chinese name Tianxi, meaning the celestial chain, sits at the geometric heart of Cassiopeiae, the fifth brightest constellation in the northern sky. It is roughly 550 light-years from Earth, though more precise modern measurements place it closer to 613 light-years away. A distance so vast that the light you see when you glance at it tonight left that star when Shakespeare was only a child, yet it blazes at an apparent magnitude of 247, bright enough to serve as a reliable guide star, a navigation landmark, a fixture of the winter sky as dependable as anything in the heavens. What you cannot see when you look at Gamma Cassiopeiae with the naked eye is the chaos embedded in that steady blue-white glow. This is a star spinning at a rate that would be physically catastrophic for most stellar objects. Its equatorial rotation velocity has been measured at approximately 432 kilometers per second. To understand what that means in felt, rather than abstract terms, consider that our own Sun rotates at the equator at roughly 2 kilometers per second. Gamma Cassiopeiae is spinning more than 200 times faster than that. At those velocities, the centrifugal force at the star's equator so nearly overwhelms its own gravity that the star is measurably, observably flattened. Its equatorial radius stretches to 10.9 times the radius of our Sun, while its polar radius collapses to only 7.9 solar radii. The star is not a sphere. It is an oblate disk of blazing gas, a spinning top of nuclear fire pinched at the poles and bulging violently outward at the waist. The consequences of that spin are visible in its spectrum and in the space immediately surrounding it. Like a spinning wet tennis ball flinging droplets in every direction, Gamma Cassiopeiae's near-critical rotation launches material from its equator outward into space. That ejected material does not escape immediately. Instead, it forms a disk, a flattened, rotating ring of hydrogen gas and dust that surrounds the star like a vast flat halo. Astronomers call this a decretion disk, distinguishing it from the accretion disks that form around compact objects consuming material, because here the disk is being shed outward by the star itself, not in falling onto it. That disk is not static, it builds over decades, then disperses. It thickens, thins and rebuilds, it pulsates and spirals, and it is, as we will see, the key to everything. Gamma Cassiopeiae is classified as a B star, a designation that carries far more history than it might initially suggest. The B refers to the spectral type, hot, blue-white, massive, with surface temperatures ranging between 17,300 and 26,500 Kelvin depending on latitude on the star's surface. The polar regions running dramatically hotter than the bloated, slower rotating equatorial belt. The E stands for emission, a feature that was, when it was first recorded, something nobody had ever seen before and nobody quite knew what to make of. The star is roughly 17 times more massive than our Sun and shines with the combined luminosity of approximately 19,000 suns. In human terms, this is not a polite or domesticated star. This is a furnace of near incomprehensible scale, burning through its hydrogen reserves at a rate that will exhaust them within a few million years. A stellar mayfly by cosmic standards, brilliant and brief. Yet what makes Gamma Cassiopeiae genuinely singular? What sets it apart not just among B stars, but among all the tens of thousands of stellar objects catalogued in the northern sky? is not its spin, not its disk, not even its luminosity. It is what came to light, in the most literal possible sense, when astronomers trained the first X-ray telescopes toward it in the mid-1970s. What they found should not have been there, and it took 50 years, 3 generations of X-ray observatories, and one extraordinarily sensitive new instrument to finally understand what was really going on. But before we get to the X-rays, we need to go back to the very beginning of the story. Back to the moment in 1866 when a Jesuit priest in Rome looked at this star and saw something in its light that nobody before him had ever described, because the mystery of Gamma Cassiopeiae did not begin in the 1970s. It began with a fingerprint, a strange glow in a spectrum, and a question that would take 160 years to fully answer. The Collegio Romano has stood at the heart of Rome since the 16th century, founded by Ignatius of Loyola, the intellectual engine of the Jesuit order, a place where philosophy, theology, and natural science were considered not contradictory pursuits, but different modes of the same search for truth. By the 1860s, the observatory perched atop the Collegio Romano was home to one of the most productive astronomers of the 19th century, a Jesuit priest named Angelo Secchi. He was born in 1818 in the town of Reggio Emilia in the flat agricultural plain of northern Italy. He became a Jesuit novice at 17, studied physics and mathematics in Rome, fled Italy during the revolutionary upheavals of 1848, spent time in the United States and England, and returned to Rome to take up the directorship of the Collegio Romano Observatory in 1850. He would hold that position until his death in 1878, and in those 28 years he would transform the discipline of astronomy from a science of positions and motions into a science of natures and compositions. Secchi's central contribution was to ask not simply where the stars are, but what they are. He understood, as only a handful of thinkers did in the mid-19th century, that light was not merely a direction indicator or a brightness marker. Light was a message. Each element in the universe absorbs and emits light at specific, characteristic wavelengths, a fact that had been demonstrated for the Sun by Joseph von Fraunhofer decades earlier, but had not yet been systematically applied to the stars. Secchi began the first large-scale stellar spectroscopic survey in history, examining the spectra of more than 4,000 stars between 1863 and 1867, working by eye before the introduction of photographic plates, translating the rainbow signatures of distant suns into a classification scheme that would eventually become the foundation of modern stellar taxonomy. Most of what he saw confirmed what was expected. The majority of stars showed dark lines in their spectra, absorption lines, where the cooler outer atmosphere of a star absorbed specific wavelengths from the hotter interior below. The pattern of those dark lines told you which elements were present, how hot the gas was, how the star was physically structured. It was a coherent, readable story. But then Secchi pointed his spectrograph at the central star of Cassiopeiae, and the story broke down. In the spectrum of Gamma Cassiopeiae, in the position where the hydrogen lines should have appeared as dark absorptions, as they did in every other hot blue star Secchi had examined, he instead found bright emission lines. The spectrum was speaking in reverse. Where other stars showed absence, Gamma Cassiopeiae showed presence. He published this observation in 1867, noting the peculiarity with the careful, restrained language of a scientist who does not quite know what to do with what he has found, and then moved on. He had thousands of other spectra to analyse. He had a classification system to build. He could not have known that the single anomalous line he had noted in the spectrum of one unremarkable-looking bright star in Cassiopeiae would eventually become the defining feature of an entire stellar class, the subject of a century and a half of argument, and the first thread in a mystery of quite staggering depth. The emission line Secchi recorded was hydrogen beta, one of the characteristic wavelengths at which hydrogen gas emits light. In normal hot stars, the hydrogen in the stellar atmosphere is cool enough relative to the interior to absorb that wavelength, to leave a dark gap in the spectrum. But in Gamma Cassiopeiae, the hydrogen was emitting. Something was energizing it. Something was causing hydrogen gas in or near that star to radiate rather than absorb, to glow rather than shadow. Secchi did not know what that something was. Neither for another 80 years did anyone else. The classification that emerged from Secchi's observation became the B designation, B for the spectral type and temperature class, E for emission. Gamma Cassiopeiae became the prototype, the defining example, the reference point for all B stars identified afterward. Today, astronomers have catalogued thousands of B stars across the Milky Way, and roughly 20% of all B-type stars qualify as B stars at some point in their lives, since many of them develop the emission signature and then lose it again as their disks build and disperse. Gamma Cassiopeiae is not the only B star, not even close, but it is the first. It is the one against which all others are measured. It is, in the precise language of astrophysics, the prototype, the explanation for the emission lines, when it finally came in the mid-20th century, was genuinely extraordinary. Those bright lines were not coming from the star's surface at all. They were coming from the decretion disk, that vast flattened ring of gas that the star's near-critical rotation was flinging outward into the surrounding space. The hydrogen in that disk, heated and energized by the star's fierce ultraviolet radiation, was glowing. The disk was fluorescing. And because the disk extended outward in the plane of the star's equator, the strength of the emission lines varied, depending on the disk's current size and density. When the disk grew thick and extended, the emission lines blazed bright. When the disk thinned or dispersed, the emission faded. The star was, in effect, wearing a luminous ring of self-generated nebula, breathing it out and drawing it back in overcycles spanning years to decades. Between 1866 and 1932, Gamma Cassiopeiae settled into a pattern of moderate emission that varied slowly and without drama. But then, between 1932 and 1942, something extraordinary happened. The star underwent what astronomers now call a shell episode, a dramatic brightening and restructuring in which the disk swelled, thickened, and partially absorbed the stellar flux, sending the apparent magnitude swinging from 1.6 all the way down to 3.4. A change of nearly 2 full magnitudes, a fourfold dimming visible to anyone who had watched Cassiopeiae long enough to know what it normally looked like. By 1942, the emission had largely vanished. The disk had essentially dissolved. The star was briefly back to being an ordinary-looking absorption line B star. Then slowly, over subsequent decades, the emission crept back. By 1981, the disk was re-established, and Gamma Cassiopeiae was once again wearing its signature glow. This variability became one of the star's defining features, and one of the reasons it attracted ongoing observation. The shell episode of the 1930s and 1940s, for all its visual drama, was ultimately explicable within the framework of B-star physics. Stars spin fast, they eject disks. Disks build and disperse. That was understood, at least in outline, by the middle of the 20th century. What was not understood, what nobody had any framework whatsoever to explain, was what happened in 1976, because in 1976, a satellite pointed its instruments at Gamma Cassiopeiae and discovered that it was glowing with X-rays. Not the mild, expected soft X-ray flux that any hot massive star might produce through its stellar wind. Something incomparably stranger. Something that, at the time, made no sense at all. The mystery was not 50 years old, as the headlines of 2026 would eventually put it. In a deeper, truer sense, it was 160 years old, rooted in the moment when Father Secchi noticed that this star's hydrogen was singing where it should have been silent, and wondered, perhaps only briefly, what could possibly be causing that. To understand why the 1976 X-ray discovery was so shocking, you need to understand what X-rays are and what produces them in astrophysical environments. X-rays are not some exotic or rare form of radiation. They are photons, particles of light, with energies roughly 1,000 to 1 million times greater than the visible photons your eye detects when you look at a star. Those high energies correspond directly to high temperatures, Only gas or plasma heated to millions of degrees can emit X-rays in significant quantities. In the structured, ordered environment of a star's atmosphere, that kind of temperature is rare and specific. It is found in stellar coronae, the tenuous outer envelopes of some stars, heated by magnetic processes to temperatures far above those of the visible surface, and in the immediate vicinity of compact objects like neutron stars and black holes, where infalling matter is compressed and heated to catastrophic temperatures before it hits the surface or crosses the event horizon. In ordinary hot massive stars, B stars and O stars, the luminous blue giants that account for a tiny fraction of the stellar population, but a disproportionately large fraction of the light in any galaxy, X-ray emission is expected, but at modest levels. The fast, powerful stellar winds these stars drive outward are filled with instabilities. Faster clumps of wind crash into slower ones, creating shocks. Those shocks heat the gas to temperatures in the range of a few million degrees, sufficient to produce soft X-rays. The X-ray luminosity expected from a typical B star of Gamma Cassiopeiae's mass and temperature, calculated from this wind shock model, is around 10 to the 31st ergs per second, a standard benchmark that held up well across a wide population of similar stars. In 1976, when astronomers examined the X-ray data from Gamma Cassiopeiae gathered by early satellites, they found something that flatly refused to match that benchmark. The star was not merely brighter in X-rays than expected, it was dramatically, inexplicably brighter, by approximately a factor of 40, not 40%, 40 times. The X-ray luminosity of Gamma Cassiopeiae came in at roughly 10 to the 32, 8 ergs per second, far beyond what windshock physics could account for, far beyond what any B star of comparable mass and temperature had any right to be producing, and the temperature of the emitting plasma was not in the few million degree range expected from wind shocks. It was sitting at somewhere between 100 million and 150 million Kelvin. That is a temperature range you encounter not in stellar winds, but in the heart of thermonuclear explosions, or in the accretion columns above the poles of magnetically channeling compact objects. This is the X-ray anomaly of Gamma Cassiopeiae, and from the moment of its discovery, it constituted one of the most resistant and provocative open problems in stellar astrophysics. The star is too bright in X-rays by a factor of 40. The plasma producing those X-rays is too hot by an order of magnitude. Both of these violations are simultaneous, consistent, and inexplicable within any framework that treats Gamma Cassiopeiae as an isolated, ordinary massive star. Something is generating an enormous amount of energy at very high temperatures somewhere in or near this system, and the question that would occupy astronomers for the next 50 years was simply, what? The initial period after the 1976 discovery was one of hypothesis generation, when the field was young enough and the data sparse enough that almost any mechanism could be seriously proposed. Could the X-rays be coming from a corona around the disk? The disk of a B star is a dense, hot, magnetized structure. Perhaps it had its own coronal heating mechanism, analogous to the solar corona, but enormously scaled up. Could the star itself have an unusual magnetic field driving reconnection events? Magnetic reconnection, the explosive rearrangement of tangled magnetic field lines, releasing stored energy as heat and radiation, is responsible for solar flares after all. A sufficiently active magnetic star might, in principle, flare at a scale that produced detectable X-rays. Could there be a companion object feeding from the disk and releasing gravitational energy as it did so? That was a third possibility, perhaps the most intuitively compelling, but also the hardest to prove since no companion had been directly observed. For the first 2 decades after the discovery, these possibilities remained approximately equally credible because the X-ray observatories of the era, the early satellites like Uhuru, Exosat, and Rossat, lacked the spectral resolution to distinguish between them. They could tell you that Gamma Cassiopeiae was emitting X-rays. They could tell you roughly how bright it was, and roughly how hot the plasma was, but they could not reveal the fine structure of the emission, the precise shape of the spectral lines, the Doppler shifts encoded in those lines, the velocity information buried in the wavelength positions. That would eventually tell you where in the system the plasma was located and what was doing the heating. What the early observations could do was reveal the variability of the X-ray emission, and that variability was itself a clue of extraordinary richness. Gamma Cassiopeia's X-ray output was not steady. It flickered and surged on timescales of minutes to hours, sometimes rising factors of 2 or 3 in less than an hour, and then subsiding equally quickly. This rapid variability was deeply inconsistent with the magnetic reconnection model as initially conceived, because reconnection events tied to the global magnetic interaction between star and disk would be expected to vary on the orbital timescale of the disk material. Hours to days, not the minute-to-minute flicker that was actually observed. The flickering looked more like what you might expect from accretion, the irregular, bursty process of clumps of gas falling onto a compact object, each clump releasing a pulse of energy as it strikes the surface. But it also looked somewhat like what you might expect from a population of magnetic flares, short, intense, and scattered in time. In 1996, a development occurred that would prove, in retrospect, to have been the conceptual key to the entire problem, even though its implications would not be fully recognized for another 30 years. Astronomers monitoring the spectroscopic binary motion of Gamma Cassiopeiae, the subtle periodic shift in the star's spectral lines, caused by its orbital dance with an unseen companion, finally pinned down the orbital parameters of that companion to a meaningful degree. The orbital period was determined to be 203.59 days, with an eccentricity of 0.26, an orbit that was distinctly non-circular, bringing the companion closer to Gamma Cassiopeiae at some points in its orbit than at others, and the mass of the companion, inferred from the amplitude of the radial velocity curve, came out at roughly 1 solar mass. That number carried an enormous range of possible identities. The companion could be a normal Sun-like main sequence star. It could be a white dwarf, the collapsed, Earth-sized remnant of a dead low-mass star, with the mass of the Sun packed into the volume of a planet. It could theoretically be a neutron star, though neutron stars would be expected to show very different X-ray signatures. The 1996 orbital measurement did not resolve the question of what the companion was, but it did firmly establish that a companion existed and that it was orbiting Gamma Cassiopeiae with a well-defined, well-measured period. Every 203.59 days it completed one orbit, every 203.59 days at closest approach, periastron. It came nearer to the B star's decretion disk. With the advent of ESA's XMM Newton X-ray Observatory in 1999 and NASA's Chandra X-ray Observatory in the same year, the precision of Gamma Cassiopeiae's X-ray portrait improved dramatically. By the 2000s, researchers were able to generate detailed X-ray spectra of the system, not just brightness measurements but genuine spectral profiles, resolving individual emission lines and measuring their shapes with enough precision to begin constraining models. And those spectra revealed two things that were simultaneously illuminating and deeply frustrating. First was that the X-ray emission contained a strong ion emission feature at 6.7 keV, the so-called ion K-alpha line, produced when highly ionized ion atoms are heated to tens of millions of degrees and emit characteristic X-ray photons as their electrons cascade through energy levels. This ion line is one of the most diagnostic features in high-energy astrophysics. Its exact energy, shape and width encode information about the temperature of the plasma, its density, the velocity of the emitting gas, and the physical environment in which the emission is occurring. In Gamma Cassiopeiae, the ion line was bright, well-resolved and clearly structured, but its width was tantalizingly ambiguous. It was too narrow to definitively confirm rapid accretion onto a compact object. It was too broad to rule it out. The second thing the new spectra revealed was a more subtle but equally provocative feature. The spectrum of Gamma Cassiopeiae showed not one but two temperature components. A very hot component at around 100 million Kelvin and a cooler component at a few million Kelvin. This two-temperature structure was difficult to explain within a single mechanism model. If you were dealing with pure wind shocks, you would expect a relatively soft, moderate temperature spectrum. If you were dealing with pure accretion onto a compact object, you might expect a hard, high temperature spectrum. But the mixture of both temperatures, bright hot component, quieter cool component, did not fit neatly into either framework. It almost looked as if two separate physical processes were contributing to the X-ray emission simultaneously. By the early 2010s, the field had consolidated around two primary theories, having eliminated or substantially discredited a number of earlier proposals. The first theory, call it the magnetic interaction model, held that the X-rays were generated by reconnection events between the magnetic field anchored in Gamma Cassiopeia's photosphere and the magnetic field embedded in or threading through the decretion disk. In this picture, as the star's field and the disk's field were carried against each other by differential rotation, they would periodically snap and reconnect, releasing bursts of energy that heated plasma to the observed temperatures. This model had the virtue of not requiring an unseen companion. The X-ray production was entirely native to the B-star system. It also plausibly explained the rapid flickery variability, since reconnection events could occur quickly and repeatedly in the turbulent disk field interface. The second theory, call it the white dwarf accretion model, proposed that the companion identified in 1996 was indeed a white dwarf, and that as it orbited through Gamma Cassiopeiae's equatorial plane, it was skimming material from the outer edge of the decretion disk and consuming it. As that material fell down the white dwarf's steep gravitational potential, from the disk to the white dwarf surface, a fall of roughly 550 kilometers over which the gas would accelerate to a substantial fraction of the speed of light. It would be compressed and heated to temperatures well in excess of 100 million Kelvin before crashing onto the surface. The resulting X-rays would be energetic, copious, and spatially associated with the white dwarf companion rather than with the B star itself. This model was deeply appealing to a subset of theorists, but it faced a persistent obstacle. The companion had never been directly detected. If it was a white dwarf, it should be largely invisible. White dwarfs emit light, but faintly, and in the harsh glare of the blazing B star at 613 light-years, the white dwarf would be unresolvable as a separate point of light. And there the debate sat, not unproductive, but genuinely stalled. For another decade, the data were sufficient to establish the problem, but insufficient to solve it. What was needed was an instrument of unprecedented precision, something that could take the ion emission line of Gamma Cassiopeiae and slice it with enough spectral resolution to read the velocity information buried inside it. Because if the X-ray emitting plasma was associated with the white dwarf companion, then as the companion orbited the B star, moving toward us then away from us in its 203.59-day orbit, the ion emission line should shift. It should Doppler shift with the orbital velocity of the companion. And if the plasma was instead associated with the B star itself, sitting in the disk-star interface, moving with the star, then the ion line should shift with the orbital velocity of the B star, which moves in the opposite direction to its companion. This was the test. This was the decisive experiment. Measure the ion line at multiple orbital phases. Watch it move. Note which object it moves with. The problem was that no X-ray observatory in existence before 2023 had the spectral resolution to do this. The Doppler velocities involved were on the order of a few kilometers per second to a few tens of kilometers per second. Subtle, precise shifts in the ion line position that required measuring the energy of individual X-ray photons to a precision of 1 part in several hundred. XMM Newton could not do it. Chandra's grating spectrometers were powerful in the soft X-ray band but not optimally configured for the 6.7 keV ion line. The test was clear. The instrument to perform it did not yet exist. In September 2023, it arrived. There is a particular kind of frustration in astrophysics that is different from any other scientific frustration. The frustration of knowing exactly what you need to measure, knowing exactly what the measurement would tell you, and simply not having the instrument to make it. Theorists can build models. Observational astronomers can push existing telescopes to their limits. But some questions require tools that simply do not exist yet, and there is nothing to do but wait, sometimes for years, sometimes for decades, while engineers and physicists build them. For the mystery of Gamma Cassiopeia's X-rays, that wait lasted approximately 47 years, from the discovery of the anomaly in 1976 to the September 2023 launch of the X-ray imaging and spectroscopy mission. XRISM, pronounced XRISM. XRISM is a joint mission of the Japan Aerospace Exploration Agency, NASA, and the European Space Agency, an international partnership that combined the technical and scientific expertise of 3 space agencies to build what is, at the time of writing, the most powerful X-ray spectrometer ever placed in orbit. It launched aboard a JAXA HDOA rocket from the Tanegashima Space Center on September 7, 2023, and carries 2 instruments: Extend, a wide-field X-ray imaging camera that produces detailed spatial maps of X-ray sources, and Resolve, a high-resolution X-ray spectrometer of a type that had never before been successfully deployed in space. Resolve is a microcalorimeter, a device of extraordinary sensitivity that measures the energy of individual X-ray photons by detecting the infinitesimally small temperature increases each photon produces when it is absorbed by a supercooled detector array. To understand why this is so powerful, consider how conventional X-ray detectors work. They count photons and measure their approximate energies, but the energy resolution is limited by the physics of how semiconductor materials respond to radiation. Conventional X-ray CCDs, the type used by XMM Newton's EPIC cameras and by Chandra's ACES detector, can measure photon energies with a resolution of roughly 100 to 200 electron volts. That sounds precise until you realize that the ion emission lines, clustered around 6.7 keV, are separated from each other by only a few tens of electron volts, and that the Doppler velocity shifts you would need to detect in Gamma Cassiopeia's ion line are encoded in wavelength shifts, equivalent to less than 10 electron volts. DDoS changes all of that. It consists of a 6x6 pixel array of X-ray absorbers, each cooled to approximately 50 millikelvin, 50 thousandths of a degree above absolute zero. When a single X-ray photon strikes one of these absorbers, it deposits its energy as heat. The temperature rise this produces is minuscule. For a 6.7 keV ion photon, we are talking about a temperature increase of roughly 1/millionth of a Kelvin, but at 50 millikelvin, that change is detectable. A transition edge sensor, a superconducting device operating exactly at the boundary between its superconducting and normal conducting states, where its electrical resistance is exquisitely sensitive to temperature, records the energy of each absorbed photon with a precision of approximately 7 electron volts. Not 100, not 200, 7. That factor of roughly 20 in spectral resolution improvement over conventional CCD detectors is transformative. It is the difference between hearing someone speak from across a noisy room and having them whisper directly into your ear. Lines that previously merged into an unresolved hump can now be separated and individually analysed. Doppler velocities of tens of kilometers per second. The kind of velocities that might betray the orbital motion of a 1 solar mass companion orbiting a 17 solar mass B star at a distance of roughly 1.6 astronomical units are now readable in the shifting positions of emission lines. The physics was always there, encoded in the light. XRISM's Resolve was finally able to read it. The operational challenges of maintaining a 36-pixel array at 50 millikelvin in the thermal environment of space cannot be overstated. The entire cryogenic chain required to keep Resolve at its working temperature involves multiple stages of cooling, from the ambient temperature of space, roughly 270 Kelvin below zero, or about 3 Celsius in shadow, down through liquid helium at 4 Kelvin, then to a mechanical refrigerator stage at sub-Kelvin temperatures, and finally to the adiabatic demagnetization refrigerators that achieve the 50 millikelvin operating point. The cryogenic system aboard XRISM carries a finite supply of liquid helium, approximately 30 litres, that limits the mission lifetime. It is a one-shot opportunity. When the helium runs out, the calorimeter warms up and Resolve's extraordinary capabilities are gone. This operational reality, the ticking clock of the helium supply, the irreplaceable precision of the instrument, was part of the context in which Yael Nazet and her collaborators at the University of Liège, together with their European, American and Japanese partners, proposed their dedicated observing campaign of Gamma Cassiopeiae. They were asking for a significant allocation of XRISM's precious time to observe a single star system at 3 separate points in its 203.59-day orbital cycle. The scientific stakes had to be clear and compelling, and they were: Nazet is a Belgian astrophysicist who has spent a substantial portion of her career working on exactly this problem. Born and educated in Liège, Belgium, she joined the group for astrophysics of high energies at the University of Liège, known by its French acronym GAPE, and turned her scientific attention to massive stars and their high-energy properties. Over more than 2 decades, she and her colleagues had been the single most productive group in the world for identifying Gamma Cas analogues, the class of stars that show the same anomalous X-ray properties as Gamma Cassiopeiae itself. Of the roughly 24 Gamma Cas analogues known by the time of the XRISM campaign, Nazet's group at Liège had identified more than half. This was not passive cataloguing, it was detective work of the most painstaking kind, searching through the observational archives of XMM Newton, Chandra, and the German Erecita satellite, looking for B stars whose X-ray spectra showed the characteristic signature of the Gamma Cas phenomenon. The anomalously high luminosity, the 100 million Kelvin plasma temperature, the ion emission feature at 6.7 keV, the rapid variability. Each new Gamma Cas analogue added a data point to the population, and the population as a whole was the statistical substrate on which any proposed physical model had to stand. A model that explained 1 star was possible. A model that explained 24 stars, spanning a range of masses, spectral types, orbital configurations and disk properties, was far more constrained and therefore far more meaningful. By the time XRISM launched, Nazet and her colleagues had done something even more decisive. They had already eliminated several of the competing theories for the Gamma Cas phenomenon. The stripped companion model, in which the companion was a normal star that had been stripped of its outer layers during a previous mass transfer episode, was effectively ruled out because it predicted X-ray properties that the observations consistently failed to produce. The neutron star model was problematic because neutron stars accreting from a B star disk tend to produce very hard X-ray spectra with characteristic pulsation signatures, and Gamma Cassiopeiae showed neither. By 2023, the field had converged on 2 surviving theories: magnetic reconnection between the B star and its disk, and accretion onto a white dwarf companion. The XRISM campaign was designed to distinguish between them. The strategy was elegant in its simplicity. If the X-ray emitting plasma is produced in the disk-star magnetic interface, it is physically associated with Gamma Cassiopeiae itself, orbiting with it, moving with its centre of mass. If the plasma is instead produced by accretion onto the white dwarf companion, it is physically associated with the companion, orbiting with the companion's motion, which is in the opposite direction to Gamma Cassiopeia's orbital motion at any given time. In the 203.59-day orbit, there are moments when the white dwarf is moving toward Earth and moments when it is moving away. Those motions, typically of order a few tens of kilometers per second, are small but, with Resolve's 7 electron-volt spectral resolution, entirely detectable in the Doppler shift of the ion emission line. The team planned 3 observations, spaced to sample distinct orbital phases across the binary's 203.59-day cycle, one in December 2024, one in February 2025, and one in June 2025. Together, these 3 observations would cover the full range of the binary's projected velocity, from one extreme to the other, providing the velocity time series needed to test the Doppler prediction. The total observing time requested was substantial. The scientific case was airtight. The helium clock was ticking, and in the data, when Nazé and her colleagues finally had all 3 observations in hand and began the spectral analysis, measuring the centroid position of the ion emission line in each spectrum, comparing the measured velocities to the known orbital solution for the binary system, the answer that had been hiding for 50 years quietly, unambiguously, and unmistakably revealed itself. I find this particular moment genuinely difficult to write about without a certain reverence. Here was a question that had been formally unanswered since 1976, a question that had occupied the careers of multiple generations of astronomers, that had generated dozens of papers proposing and testing competing mechanisms, that had resisted every previous instrument's best efforts to resolve it. And the answer came not from some dramatic breakthrough or paradigm-shattering theoretical insight, but from the patient, meticulous application of a better thermometer, a 36-pixel detector cooled to 50,000ths of a degree above absolute zero, orbiting Earth at an altitude of roughly 550 kilometers, measuring the energy of individual X-ray photons one at a time, whispering the orbital velocity of an invisible white dwarf in data that would have been unreadable to every instrument that preceded it. The ion emission line moved. It moved between the 3 observations. It moved in perfect synchrony with the orbital motion of Gamma Cassiopeia's companion, not with the B star itself. With the companion, the X-rays were coming from the white dwarf. Science rarely happens in a single moment of revelation, however satisfying it is to present it that way. The answer that XRISM delivered in 2025 was the terminus of a journey that for Yael Nazé had begun more than 20 years earlier, and that for the broader community of researchers who had worked on the Gamma Cars problem stretched back through multiple generations to the discovery of the anomaly itself. To understand why this result carries the weight it does, why astronomers who had worked on this problem for decades reacted to the XRISM data not with academic detachment, but with something closer to relief, you need to follow the human thread of this story, which is in some ways more revealing than the astrophysics itself. Yael Nazé completed her doctoral thesis at the University of Liège in the early 2000s, working on massive stars and X-ray binaries. She entered the field at a time when the Gamma Cass phenomenon was already recognized as a serious and unresolved problem, but when the tools available to attack it were limited to the comparatively blunt instruments of XMM Newton and Chandra. The first XMM Newton observation of Gamma Cassiopeiae had been taken in 2001, and the data were rich by the standards of the time. Far better than anything that had come before, but still insufficient to distinguish between the 2 surviving models. The ion line was there, its shape was suggestive, but the velocity information could not be extracted from a spectrum with 150 electron-volt resolution, when the signal you were looking for was encoded in a shift of less than 10 electron-volts. What Nazé and her Liège colleagues could do with XMM Newton was systematic work. They could survey. They could build the population of Gamma Cass analogues into something statistically meaningful, moving from the single prototype, which might always be dismissed as an isolated curiosity, to a genuine stellar class with definable properties and consistent characteristics. Every new Gamma Cass analogue they identified was another constraint on the models. The physical mechanisms responsible for the anomalous X-rays had to work not just for one star but for all of them, across the full range of their physical parameters. This systematic work required not just observational skill, but a particular kind of persistence that is, I think, underappreciated in the popular narrative of science. Most of the papers Nazé and her group produced in the 2000s and 2010s were not announcing dramatic discoveries. They were building scaffolding, ruling out, constraining, measuring the properties of one new Gamma Cass analogue, comparing it to the population, noting where the models succeeded and where they struggled. It was the kind of work that does not generate press releases or inspire dramatic documentary recreations, but without which the final discovery could not have happened. because you cannot interpret a definitive result in a population you have not yet characterized. There was also a personal geography to this work that I find worth noting. The University of Liège sits in the Meuse Valley in eastern Belgium, a city built around a river bend in the foothills of the Ardennes. It is not, in the conventional imagination of space science, the sort of place from which great astronomical discoveries emerge. The public narrative of astrophysics tends to situate itself at the great American observatories, Palomar, Keck, the Space Telescope Science Institute, or at the European Space Astronomy Centre outside Madrid, or at the Harvard-Smithsonian Centre for Astrophysics in Cambridge, Massachusetts. Liège is a working city, an industrial city historically, a university city with a long tradition of applied science, but not one that features prominently in the mythology of deep space exploration. Yet it was from Liège that more than half of all known Gamma Cas analogues were identified. It was a Liège-led team that progressively narrowed the theoretical field from 5 or 6 competing models down to 2, and it was Nazé herself, leading the XRISM observing campaign with the accumulated expertise of more than 2 decades of work on this specific problem, who designed the 3-observation strategy that would finally deliver the decisive data. There is something deeply appropriate about the fact that the scientist who solved the mystery was not a newcomer dazzled by a single spectacular observation, but someone who had spent 20 years building the context in which that observation could be understood. When the first XRISM observation was taken in December 2024, Nazi and her team had to wait. The resolve spectrometer had to complete its observation. The raw data had to be telemetred down to Earth and processed through the calibration pipeline. The spectral fitting had to be performed, and even then, a single observation was not the answer. It was one data point in a 3-point experiment. The iron line at a single orbital phase tells you a velocity but not a trend. You need the trend to distinguish between the models. You need to see the line shift. The February 2025 observation was the second data point. When Nazé and her colleagues compared the iron line centroids from the December and February observations, they saw a shift. Not a marginal, barely significant shift that might be attributed to instrumental effects or statistical noise. A real shift, with a statistical significance that left little room for doubt. The plasma was moving, and the direction and magnitude of the shift matched the orbital motion of the white dwarf companion, not the B star itself. To within the measurement uncertainties, the June 2025 observation completed the picture, with the white dwarf at a different point in its orbit, having moved through another portion of its elliptical path around the B star. The iron line shifted again, in the direction, and by the amount predicted by the white dwarf accretion model. 3 observations, 3 orbital phases, 3 consistent, well-measured velocity shifts. The chi-squared statistic of the fit between the observed velocities and the white dwarf orbital prediction was, in the language of the paper Nazé and her colleagues published in Astronomy and Astrophysics in March 2026, highly significant. In the language of a scientist who has waited 20 years for this answer, it must have felt like something else entirely. I have read the acknowledgements section of that paper several times. It is written in the careful, formal language of scientific publications, a list of funding agencies, telescope operators, data reduction software packages, and collaborating institutions. Between those lines of professional courtesy, there is a sentence that Nazé delivered to the European Space Agency's press office when the result was announced that I think captures the human dimension of this story better than any technical summary could. There has been an intense effort to solve the mystery of Gamma Cas across many research groups for many decades, she said. And now, thanks to the high-precision observations of XRISM, we have finally done it. Finally done it. Those 3 words carry the weight of 50 years of observation, of careers spent on a single stubborn question, of instruments launched and operated, and eventually retired, without quite having sufficient precision to close the case. They carry the weight of every graduate student who has written a thesis section on the Gamma Cassiopeiae phenomenon and concluded it with some variant of "the physical mechanism remains unknown." They carry the weight of the astronomers who first detected the anomaly in 1976 and are no longer alive to see its resolution. But even in that moment of resolution, there was another question emerging, because the white dwarf accretion model did not resolve the mystery cleanly, in the way that a mathematical proof resolves to a single final answer. It resolved it into a deeper question, one that NASA herself identified in the same paper, and that opens onto territory that may require another generation of instruments to fully explore. The nature of that deeper question brings us to the stakes of this discovery, and they are considerably higher than the question of one star's X-ray output. When Yael Nazay and her team announced that Gamma Cassiopeiae's anomalous X-rays were produced by accretion onto a white dwarf companion, they were not simply solving one astronomical puzzle. They were confirming the existence of a stellar population that had been theoretically predicted for decades, but had never been clearly identified. And that confirmation, once properly situated in the broader landscape of stellar astrophysics, reveals itself as something considerably more consequential than a single system's solved mystery. To understand why, we need to think about binary stars, which is to say, we need to think about the majority of stars in the Milky Way. It is a striking and underappreciated fact that most stars do not live alone. The Sun is exceptional in its solitude. Surveys suggest that somewhere between 40 and 50% of Sun-like stars exist in binary or higher multiple systems, and that fraction climbs steeply with stellar mass. Among B-type stars, the class to which Gamma Cassiopeiae belongs, the binary fraction approaches 70 to 80%. Among O-type stars, even more massive and hotter, the number climbs further still. The default condition for a massive star is not isolation, but companionship. A gravitational partnership that shapes both stars' evolution from birth through to death. When a binary system consists of two stars of significantly different masses, their evolutionary timelines diverge. The more massive star burns through its hydrogen faster, expands into a giant and undergoes the end stages of stellar evolution: shell burning, instabilities, mass loss, on a timescale of millions of years, while its lower mass companion continues quietly on the main sequence, still relatively young and undistorted. When the more massive star reaches its end, the nature of that ending depends on its initial mass. Stars below roughly 8 solar masses shed their outer layers gently over tens of thousands of years, leaving behind a white dwarf, a dense, inert sphere of carbon and oxygen roughly the mass of the Sun, compressed into an object the size of Earth. Stars above roughly 8 solar masses undergo a core collapse supernova, leaving behind a neutron star or, for the most massive cases, a black hole in a binary system. This asymmetric evolution creates a situation that has fascinated and challenged theorists for decades: a massive, still young, still active companion to a dead stellar remnant. The white dwarf sits in its orbit, saying nothing, emitting nothing particularly noticeable. Meanwhile, the younger star evolves, perhaps developing the rapid rotation and decretion disk of a B star, flinging material outward into the space around it. And if that disk extends outward far enough, if the white dwarf's orbit brings it close enough, the disk material will begin to flow toward the white dwarf, drawn by gravity, spiraling inward and eventually forming an accretion stream or accretion disk around the compact object. As that material falls down the white dwarf's gravitational potential well, from the outer disk, at perhaps 1 or 2 astronomical units from the B star down to the white dwarf's surface, at a radius of roughly 7 frozen kilometers, it heats catastrophically. The X-rays are the sound of that fall, the gravitational potential energy of the accreting material, converted to heat, radiated outward as high-energy photons. This picture, a B star orbited by an accreting white dwarf, had been discussed in the theoretical literature as a natural product of binary stellar evolution. It was not controversial in theory, it made perfect sense. If massive binary stars evolve asymmetrically, and if the more massive component eventually becomes a white dwarf, and if the surviving companion develops B-star properties with a disk, then B plus white dwarf systems should exist and should show accretion-generated X-rays. The question was not whether they should exist, but how many there should be, and which known systems belonged to this class. Here the observations pre-XRISM had conspired to create a problem rather than a solution. The Gamma Cassiopeiae phenomenon, with its 100 million Kelvin plasma and its 40 times anomalous X-ray luminosity, had been identified in roughly 24 stars. But identifying a phenomenon in a star does not automatically identify the mechanism. For years, the Gamma Cassiopeiae phenomenon could plausibly have been entirely magnetic, a disk-star magnetic interaction that produced hot plasma without any compact companion being necessary. If that magnetic model were correct, then the Gamma Cassiopeiae analogues were not a population of B plus white dwarf binaries. They were simply unusually magnetically active B stars. The XRISM result eliminates that ambiguity for Gamma Cassiopeiae itself, and by extension strongly supports the same interpretation for the entire Gamma Cassiopeiae analog class. If the prototype's X-rays are produced by white dwarf accretion, the presumption is that the same mechanism operates in the analogues, a presumption that Nazé and her colleagues describe as highly motivated, given the consistent spectral properties of the class. The Gamma Cassiopeiae analogues are, most likely, all B plus white dwarf binary systems, all 24 or so of them, and now the implications begin to branch, because 24 known Gamma Cassiopeiae analogues in a galaxy of hundreds of billions of stars is a spectacularly small number. The theoretical models of binary stellar evolution had predicted that B plus white dwarf systems should be reasonably common, perhaps more common than they appear. More specifically, theoretical models had predicted that the B plus white dwarf phenomenon should be most prevalent among low-mass B stars, where the evolutionary timescales and mass transfer efficiencies favour the formation of this kind of pairing. But the observational sample tells a different story. Gamma Cassiopeiae analogues tend to cluster among massive B stars, the hotter, more luminous, more rapidly spinning end of the B star distribution, and they represent roughly 10% of massive B stars, not the higher fraction that theory had predicted. This is the binary evolution discrepancy, the disconnect between what theoretical models of stellar binary evolution predict about the B plus white dwarf population and what the observational census of Gamma Cassiopeiae analogues actually reveals. The discrepancy is not small, it is not a minor calibration issue. The models predicted a population concentrated in low-mass B stars. The observations show one concentrated in high-mass B stars. The models predicted a higher overall fraction. The observations show a lower one. Something about how massive binary stars exchange mass, interact, and evolve is not captured correctly by the current generation of theoretical models. What that something is, nobody yet knows for certain. The most likely explanation, according to Nazé and her colleagues, lies in the efficiency of mass transfer between the two stars during the first evolutionary episode. When the original primary star was swelling into a giant and beginning to shed its outer layers onto its companion. In the standard models, this mass transfer is treated as relatively efficient. Most of the material shed by the primary lands on the secondary, making it more massive and spinning it up, potentially giving it the rapid rotation that would eventually make it a B star. But if the mass transfer is substantially less efficient than the models assume, if significant amounts of material are expelled from the system rather than accreted, then the secondary star does not gain as much mass or angular momentum. The B phenomenon is suppressed in lower mass stars, and the surviving population of B plus white dwarf systems is shifted toward higher mass primaries, where the original mass ratios were more extreme. This is not an abstract or academic discrepancy. The efficiency of mass transfer in massive binary systems is one of the key input parameters for models of binary compact object formation, the formation of neutron star and black hole binaries, the systems that eventually merge and produce the gravitational wave signals detected by the LIGO and Virgo observatories. The same physical processes that create B+ white dwarf systems also, on longer timescales and with more massive stars, create the progenitors of neutron star mergers and black hole mergers. A systematic error in how we model mass transfer efficiency does not merely affect our understanding of B stars. It propagates through to every binary evolution calculation in the field. It affects how we estimate merger rates. It affects how we interpret the distribution of gravitational wave sources detected by LIGO. It affects how we model the chemical enrichment of galaxies, which is substantially driven by the supernovae of massive stars. I want to be careful here not to overstate the case. The XRISM result does not directly overturn gravitational wave astrophysics. The connection is real but indirect, a chain of inference that requires several steps of extrapolation before it reaches the merger rate calculations that LIGO scientists care about. But it is a real connection, and it is the kind of connection that makes the Gamma Cas result feel, to me, considerably larger than the question of one star's X-ray spectrum. This is not a story about resolving a 50-year-old mystery in an obscure corner of stellar astrophysics. This is a story about finding an error, or at least a limitation, in the models we use to understand how massive stars live, die, and interact with each other throughout the universe. And that matters enormously. The gravitational wave detectors are listening to the universe's deepest past right now, detecting the mergers of black holes and neutron stars at cosmological distances. Every merger they detect originated as a binary star system. Two massive stars born together, evolving together, exchanging mass, possibly losing companions to supernovae, eventually collapsing into compact objects that spiral together over billions of years. The binary evolution pathway that produces those mergers runs through exactly the kind of mass transfer physics that the Gamma Cas discrepancy challenges. When Nazé and her collaborators say, at the end of their paper, that solving the Gamma Cas mystery opens new avenues of research and suggests a revision of binary evolution models, particularly regarding the efficiency of mass transfer, they are pointing at one of the most consequential open problems in modern astrophysics. There is something that I find genuinely vertiginous about this. The idea that a star you can see with your naked eye on any clear night in the northern hemisphere, the central point of the familiar W of Cassiopeiae, 613 light-years away, visible since before humanity had a written language, contains encoded in its X-ray emission information about the processes that ultimately produce the gravitational wave signals that pass through every human body on Earth every time LIGO detects a merger event. The universe is a single interconnected system, and the threads that connect its phenomena run in unexpected directions. Let us slow down here and be precise about what XRISM actually measured, because the precision matters and the details are genuinely illuminating in ways that go beyond the headline result. The Resolve instrument's 3 observations of Gamma Cassiopeiae, taken at orbital phases selected to maximize the baseline in projected velocity, produced X-ray spectra of unprecedented quality in the 6 to 7 keV energy range. This energy range is dominated by the emission lines of highly ionized iron, specifically the helium-like ion line complex at around 6.67 keV and the hydrogen-like ion line at around 6.97 keV, as well as a fluorescence feature that can appear between them under certain conditions. In the CCD resolution spectra from XMM Newton and Chandra, these features blended into a broad, somewhat asymmetric peak that could be fitted with various temperature models, but could not be resolved into individual lines with precise centroid positions. In the Resolve spectra, with their factor of 20 improvement in energy resolution, these lines are resolved cleanly and their positions can be measured with enough precision to detect velocity shifts of order a few kilometers per second. The measured velocity shifts between the 3 observations, December 2024, February 2025, and June 2025, were consistent with the motion of Gamma Cassiopeiae's companion through its 203, 59-day orbit with an eccentricity of 0.26. The centroid velocity of the ion emission lines shifted by a total of roughly the order expected for the companion's projected orbital velocity at those phases, and the direction of the shift was consistent with the companion approaching Earth in one observation and receding in another, tracing a portion of the elliptical orbit. The statistical significance of the velocity variation between observations was high, sufficiently high that random spectral noise or calibration uncertainties could not plausibly account for it. More specifically, the paper by Nazé and collaborators notes that the velocities measured in the resolved spectra follow the orbital motion of the companion rather than the B star itself. This is the key discriminating measurement. In the binary system, the B star and its companion orbit their common centre of mass, moving in opposite directions at every point in the orbit. At any given orbital phase, the B star is moving one way, and the companion is moving the other way. When the ion line's measured velocity matches the companion's predicted velocity and anti-correlates with the B star's predicted velocity, the X-ray emitting plasma is physically associated with the companion. This is not an ambiguous result. It is a direction measurement. The plasma is with the companion, but the XRISM data contains additional information beyond the centroid velocity, and that additional information begins to constrain not just which object hosts the X-ray emission, but how the emission is physically generated, the width of the ion emission lines, how broad they are relative to their pure Doppler thermal width, encodes information about the bulk velocities of the emitting plasma. A non-magnetic white dwarf accreting through an accretion disk would be expected to show broad emission lines, because the material in the inner regions of the disk would be moving at a substantial fraction of the orbital velocity at the white dwarf's surface. Velocities of thousands of kilometers per second, which would produce enormously broadened spectral lines. But the resolved spectra do not show broad lines. The ion emission feature has a width of the order of 200 kilometers per second, which is consistent with material flowing onto the white dwarf's poles, but which is dramatically narrower than what would be expected from disk accretion reaching the inner regions. This narrowness points to a specific physical scenario. The white dwarf is likely magnetic. In magnetic white dwarfs, a well-established class that includes the so-called AM Hercules stars and intermediate polars. The white dwarf's magnetic field is strong enough to truncate the accretion disk at some distance from the white dwarf's surface, preventing material from spiralling all the way down to the inner disk radii where velocities would be extreme. Instead, the material is captured by the magnetic field at the disk truncation radius and is channeled along field lines toward the white dwarf's magnetic poles, flowing in a directed stream that impacts polar caps at velocities determined by the fall from the truncation radius, rather than from the inner disk edge. The resulting emission lines are narrower, the impact velocity is lower, and the X-ray spectrum has a characteristic shape that differs from non-magnetic accretion. The characteristic X-ray emission temperature of Gamma Cassiopeiae, around 100 to 150 million Kelvin, is consistent with the kind of accretion column above the magnetic poles of a white dwarf, where the accreting material, compressed and heated as it slows and stops, reaches temperatures in precisely this range before the energy is radiated away as X-rays. The consistency between the observed temperature, the measured line width, and the magnetic white dwarf scenario is not proof in any rigorous sense, but it is a coherent, self-consistent picture that hangs together across multiple independent observational diagnostics, in a way that competing models do not. It is worth pausing here to appreciate the chain of evidence that has been assembled. Start with the 1866 observation by Secchi, a single anomalous emission line that tells you the star has a disk. Add the 1976 X-ray discovery, an anomalously bright, anomalously hot X-ray source that tells you something extraordinary is happening in the system. Add the late 1990s orbital measurement, a 203, 59-day binary period with a 1 solar mass companion that tells you there is an unseen partner orbiting in the system. Add the 2 decades of XMM Newton, Chandra and Erisita observations that tell you the X-ray spectrum's general properties, and rule out several competing models. Add the XRISM resolve observations that measure the ion emission line velocity as a function of orbital phase, and tell you the X-ray plasma moves with the companion. Add the line width measurements that tell you the companion is likely magnetic. Each observation is a layer, adding specificity and constraining the solution until you arrive at a picture that is not merely consistent with the data, but that the data demands. The white dwarf companion of Gamma Cassiopeiae is probably magnetic. It has a mass of roughly 1 solar mass. It is orbiting Gamma Cassiopeiae in an elliptical orbit with a semi-major axis calculated at somewhere in the vicinity of 1.5 to 2 astronomical units, a separation comparable to the distance between the Sun and Mars. As it orbits, it intercepts material from Gamma Cassiopeiae's decretion disk. That material is captured by the white dwarf's magnetic field at the disk truncation radius, probably at a few white dwarf radii, or somewhere between 50,000 and 100,000 kilometers from the white dwarf center, and channeled along field lines to the polar regions. There, it strikes the surface and heats the accreting gas to temperatures in excess of 100 million Kelvin, producing the X-ray emission that has been puzzling astronomers since 1976. The white dwarf itself is roughly the size of Earth, radius approximately 7,000 kilometers. It is almost certainly not composed primarily of hydrogen or helium, since the original star from which it formed was likely more massive than the Sun, and would have completed helium burning, leaving a carbon-oxygen white dwarf. Its magnetic field strength is unknown, but is probably of order 10 to 100 million Gauss to produce the disk truncation implied by the line widths. For reference, the Earth's magnetic field is roughly 0.5 Gauss. The strongest steady magnetic fields ever produced in a laboratory are around 45 Tesla, or roughly 450,000 Gauss. The white dwarf's field is probably stronger than the strongest laboratory magnets by a factor of hundreds to thousands. It is a profoundly exotic object, yet despite all of this, it is essentially invisible to optical and infrared telescopes. Sitting next to a star 19,000 times more luminous than the Sun, and being itself a cooling stellar remnant whose luminosity has faded over the billions of years since it formed, the white dwarf contributes a negligible fraction of the system's visible light. We cannot see it. We can only infer it, from the orbital wobble it induces in the B star's spectral lines, from the X-rays it generates as it consumes the disk, and now definitively from the Doppler motion of those X-rays, as tracked by the most sensitive X-ray spectrometer ever placed in orbit. There is a broader lesson in this invisibility. A significant fraction of the universe is composed of objects that do not announce themselves in visible light. White dwarfs, neutron stars, and black holes that sit dark and quiet in their orbits until some circumstance brings them into contact with infalling material, and they briefly reveal themselves through the X-rays, gamma rays, or radio waves of accretion. Gamma Cassiopeiae's white dwarf companion is one of these quiet presences, dark, dense, gravitationally commanding, hidden behind the glare of its spectacular companion star, until XRISM finally gave astronomers the tools to hear it through the noise. How many other B stars have white dwarf companions that are generating anomalous X-ray emission, waiting to be identified? The current Gamma Cas analog sample contains roughly 24 known objects, but the selection effects of X-ray surveys are severe. You can only identify Gamma Cas analogs if you point an X-ray telescope at the right B stars, with enough exposure time to detect the anomalous X-ray signature. The true population of B+ white dwarf systems in the Milky Way is certainly larger than 24. How much larger is one of the key open questions that the XRISM result motivates. Nazay and her colleagues estimate that Gamma Cas analogs represent roughly 10% of massive B stars. Since massive B stars are a specific subset of the full B star population, and since the full B star population comprises roughly 20% of all B stars, and since the Milky Way contains of order a few 100 million B-type stars across its disk and halo, the arithmetic suggests that the total population of B+ white dwarf systems in the galaxy might number in the hundreds of thousands. Most of them would be detectable only if a sensitive X-ray observatory happened to observe them, and most of the Milky Way has never been surveyed at sufficient X-ray sensitivity to detect Gamma Cassiopeiae-type emission at distances beyond a few kiloparsecs. The Erisita All-Sky X-ray Survey, which mapped the entire sky in X-rays in unprecedented depth between 2019 and 2022, is the most powerful tool yet assembled for finding new Gamma Cassiopeiae analogues across the galaxy. Early analyses of Erisita data, cross-matched against catalogues of B stars, have already identified candidate Gamma Cassiopeiae analogues at greater distances than any previously known. The full exploitation of the Erisita archive, particularly in conjunction with the characterization of the Gamma Cassiopeiae phenomenon, now firmly established by the XRISM result, will likely double or triple the known Gamma Cassiopeiae analog sample over the coming decade. But here we encounter the third open question that runs through this story, the one that will most tax the next generation of theorists and observers. If the Gamma Cassiopeiae analog population is larger than currently known, and if those systems are systematically concentrated among massive B stars rather than low-mass ones as theory predicts, then the binary evolution models that predict their properties need to be revised. But revised how? Which physical processes in the models are wrong? Is it the mass transfer efficiency, as Naze and colleagues suggest? Is it the disk-companion interaction physics that determines how much material the white dwarf actually accretes? Is it the initial mass ratio distribution of massive binaries which sets up the later evolutionary pathways? Is it some combination of all of these? These are not small questions. They are the kind of questions that define research programs for entire subfields of astrophysics. And the XRISM result is not merely the end of one research program, the program that sought to explain Gamma Cassiopeiae's X-rays. It is the beginning of several others. The paper in Astronomy and Astrophysics that announced the XRISM result was published in March 2026, but its implications are still unfolding in the astronomical community and will continue to do so for years. The immediate consequence is the establishment of a new and precisely defined stellar class, B stars orbited by accreting magnetic white dwarfs. This is not a redefinition or a reinterpretation of a previously known class. It is the identification of a class that had been theoretically predicted but observationally elusive for decades. A population of objects whose existence had been inferred from evolutionary models, but which had never been definitively and directly confirmed. The confirmation changes things. When a class is definitively established, it becomes available as a laboratory for astrophysics, a set of objects with known physical properties that can be used to test and calibrate models. The Gamma Cassiopeiae analogues are now definitively B+ magnetic white dwarf systems. That means every observation of any Gamma Cassiopeiae analogue is now interpretable within a specific physical framework. The X-ray variability patterns, those minute-to-minute flickers that had seemed so puzzling in the context of ambiguous models, can now be analysed as the variability signatures of magnetically channeled accretion. The spectral shapes can be compared to models of polar cap accretion on magnetic white dwarfs. The population statistics can be compared to binary evolution predictions with specific, testable assumptions about mass transfer efficiency. The next generation of X-ray missions will play a central role in this exploitation. XRISM itself continues operating. The helium supply is finite but not yet exhausted as of the time of writing, and the mission is expected to continue delivering high-resolution spectroscopy of astrophysical sources for at least several more years. Follow-up observations of Gamma Cassiopeiae itself at additional orbital phases and dedicated resolve campaigns targeting the brightest Gamma Cassiopeiae analogues will provide the population-level velocity data needed to confirm that the white dwarf accretion mechanism operates universally within the class, not merely in the prototype. Beyond XRISM, the new Athena mission, the next major European X-ray observatory, planned for launch in the 2030s, will offer a combination of collecting area and spectral resolution that will transform the study of B+ white dwarf systems at greater distances. New Athena's proposed X-ray integral field unit spectrometer, a microcalorimeter array conceptually similar to Resolve, but with a larger field of view and improved energy resolution, will enable Gamma Cassiopeiae orbital velocity studies for objects too faint for XRISM's 36-pixel detector. Combined with the large collecting area of New Athena's mirror assembly, this will push the detectable Gamma Cassiopeiae analog population out to distances several times greater than currently achievable, dramatically expanding the sample size available for binary evolution statistics. The Erisita Survey Archive, meanwhile, is a resource that has barely begun to be mined. The All-Sky X-ray survey completed by Erisita in 2022 represents the deepest, most complete map of the X-ray sky in history, and cross-matching that map against the large catalogues of B stars now available from ground-based spectroscopic surveys and from the Gaia Astrometric mission's photometric data will yield candidate Gamma Cassiopeiae analogues at unprecedented numbers. Each candidate will be a new data point in the binary evolution census, a new system whose properties can test the models. On the theoretical side, the XI result provides a new observational anchor for binary evolution models, current stellar evolution codes, the sophisticated computational frameworks that simulate how binary stars exchange mass, lose angular momentum, and interact over millions of years, can now be tested against a well-characterized observational sample of B+ white dwarf systems. The discrepancy between the predicted mass distribution of Gamma Cassiopeiae analogues concentrated toward low-mass B stars in the models, and the observed distribution concentrated toward high-mass B stars in the data, is a specific quantitative signal that good theoretical models need to reproduce. Getting it right will require adjustments to the mass transfer physics, and those adjustments will propagate through to predictions for neutron star and black hole binary formation rates. This is where the connection to gravitational wave astronomy becomes concrete. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its counterparts Virgo and Cagra have, since their first detection in September 2015, accumulated a catalogue of binary compact object mergers that provides an extraordinary window into the populations of neutron stars and black holes in the universe. Each detected merger is the endpoint of a binary evolution pathway. The rates of different types of mergers, binary black holes, binary neutron stars, mixed black hole neutron star mergers, depend sensitively on the binary fraction of massive stars, the distribution of mass ratios, and the efficiency of mass transfer during the interactions that create the compact binary precursors. Current binary population synthesis models, the theoretical frameworks used to translate stellar physics into predicted merger rates, use mass transfer efficiency parameters that are, as the Gamma Cassiopeiae discrepancy suggests, not fully calibrated by observation. A systematic revision of those parameters, motivated by the B+ white dwarf population data, could shift the predicted merger rates by factors of several, potentially changing how we interpret the LIGO event catalogue and how we model the long-term evolution of massive star populations in galaxies of different types. I will not claim that the Gamma Cassiopeiae mystery, now solved, will directly produce new gravitational wave predictions in the near future. The chain of inference is long, and each link introduces its own uncertainties, but I will say that the resolution of this mystery has exposed a specific, well-defined gap in our theoretical understanding of binary star evolution, and that gap is not confined to the subfield of B-star physics. It threads through the entire machinery by which massive binary stars produce the compact objects that LIGO is hearing merge. That is not a connection to be dismissed. There is also an aspect of the Gamma Cassiopeiae result that speaks to a question much closer to home than gravitational wave astronomy. The question of how stellar winds, mass transfer, and the cycling of matter through binary systems influence the chemical composition of galaxies over cosmic time. When a massive star loses mass through a stellar wind, that mass enters the interstellar medium, enriching it with the nuclear process materials that the star has been synthesizing in its core and shells. When the same process occurs in a binary system, with mass transfer altering both the rates and the products of that mass loss, the chemical enrichment histories of galaxies become more complex and more interesting. Getting the mass transfer physics right affects how we model the abundances of elements – carbon, oxygen, iron, silicon – in the gas and dust from which future generations of stars form. The periodic table of the elements, as written by astrophysics, has binary star evolution as one of its key chapters. The Gamma Cass analogues are, in this sense, not merely laboratories for X-ray astrophysics. They are windows into the chemistry of the galaxy. Each B+ white dwarf system represents a snapshot of a mass transfer episode that, in the past, redistributed matter between two stars and, by doing so, altered both their subsequent evolution and the composition of their surroundings. Reconstructing the history of those episodes, using the present-day properties of Gamma Cass systems as the constraint, is a program that touches the deepest questions about how the universe became chemically complex enough to form planets, continents, oceans, and living observers who notice a strange emission line in a blue star and spend 160 years trying to understand what it means. The orbital period of Gamma Cassiopeia's binary system is 2-3, 59 days. That is how long it takes the white dwarf to complete one revolution around its companion. In that time, slightly more than 6 months, the white dwarf will have consumed a calculable amount of material from the decretion disk, generated a calculable number of X-ray photons, and moved precisely through the portion of its orbit that XRISM's 3 observations sampled. The universe keeps its own schedule, and sometimes the patience required to read that schedule is measured in decades. Father Angelo Secchi pressed his eye to the eyepiece of the spectrograph atop the Collegio Romano in 1866 and saw something odd in the spectrum of a star in Cassiopeia. He noted it, he published it, he moved on. He could not have known that the odd thing he saw, a bright hydrogen line where a dark one should have been, would still be unexplained, not fully explained, 160 years later. He could not have known that it would take the development of rocketry, the construction of X-ray observatories in space, the invention of superconducting microcalorimeters cooled to temperatures lower than any naturally occurring environment in the known universe, and the career work of at least 3 generations of astrophysicists to follow the thread he had left behind, science. When we describe it, in the clean arcs of textbooks and documentaries, tends to move from question to answer in a satisfying directed line. The reality is messier, slower, and in some ways more profound. The reality is that a question raised by one human in one place and time can travel through the decades like a message in a bottle, picked up by different hands, turned over, partially read, set down again, until eventually someone comes along with the right instrument at the right moment to read it to the end. The question was the same question it had always been. The stars that asked it, Gamma, Cassiopeiae, blazing in the north, shedding its equatorial ring of hydrogen, feeding its invisible hungry companion, was the same star it had always been. What changed was our ability to listen. There is something in this story about the nature of patience that I think is easy to miss when the headline announces the mystery solved. The patience was not passive. Every generation that worked on the Gamma Cass problem without resolving it was nevertheless necessary for the resolution. The spectroscopists who first measured the binary orbital period in the 1990s gave Naze and her team the orbital solution that the XRISM velocities could be tested against. The theorists who proposed, tested, and eliminated competing models over 4 decades left only 2 standing by the time XRISM launched, narrowing the field to the point where a single campaign of 3 observations could decide between them. The engineers who spent years developing the microcalorimeter technology that made resolve possible were solving a different problem entirely. They were not thinking about Gamma Cassiopeiae, but their solution turned out to be the exact key the stellar mystery required. This is how the best science actually works. not in isolated strokes of genius, but in long, collaborative, multi-generational accumulation, each piece of work building on the last, each generation standing on the shoulders of the previous one, until the accumulated height is enough to see over the wall that previously blocked the view. It is unglamorous by the standards of narrative drama. It is, I think, genuinely beautiful by the standards of what human beings are capable of when they commit to a question long enough. What strikes me most forcefully about the Gamma Cassiopeiae result is not the answer, spectacular as that answer is, but the question that the answer immediately generates. If B+ white dwarf systems are more concentrated among massive B stars than the models predict, and if that concentration is a signature of mass transfer inefficiency in the evolutionary histories of these systems, then the next question is whether that inefficiency is universal or contextual. Does it depend on the initial mass ratio, on the orbital separation, on the age of the binary system, on the metallicity of the environment in which the stars formed, on some combination of all of these? These are not questions that XRISM alone can answer. They are questions that will occupy theorists and observers for another generation, and perhaps beyond. And perhaps beyond Gamma Cassiopeiae specifically, the question opens into something larger and more unsettling. We have identified roughly 24 B+ white dwarf systems in the Milky Way with certainty, and we suspect the population is in the hundreds of thousands. That is a lot of hidden white dwarfs, invisible in optical light, quietly consuming their companions' disk material in the dark, generating X-rays that only the most sensitive instruments can detect. They are part of the galaxy's hidden architecture, the silent, dense, dead objects whose presence reshapes the lives of the stars around them without ever being seen directly. What other invisible presences are out there, shaping the evolution of visible stars in ways we have not yet accounted for? What other anomalies are sitting in the data archives of X-ray telescopes, waiting for a better spectrometer to reveal the motion of a hidden companion? The history of astronomy is, in a deep sense, the history of discovering that the visible universe is a small fraction of what exists. Planets were unseen until orbits betrayed them. Dark matter remains unseen despite decades of indirect evidence. The compact companions of binary stars are invisible in the glare of their luminous partners. Gamma Cassiopeia's white dwarf, a 100 million Kelvin X-ray machine, invisible to every optical telescope on Earth, hidden beside a star 19,000 times more luminous than the Sun, betrayed at last by the tiny shift of an ion emission line measured by a detector operating at 50,000ths of a degree above absolute zero. This is not an exception to the pattern. It is the pattern. Somewhere right now, there is a student, perhaps in Liège, perhaps in Tokyo, perhaps in some city that does not yet have a university, who will look up at Cassiopeiae on a clear winter night and feel the pull of it. Not just the pull of beauty, though it is beautiful. The pull of a question. The feeling that the light coming from that W of stars is carrying information we have not yet learned to read. That student does not yet know what instrument they will build, or what anomaly they will find, or what hidden companion they will unmask. But the question is already there, orbiting in the sky, waiting. Secchi left it there. In 1866, Nazé and her team took it one horizon further, in 2026. The star at the centre of the W is still spinning, still shedding its disk, still feeding the invisible fire beside it, still blazing with X-rays that tell the story of a hidden world if only you have the ears to hear it. The universe doesn't announce itself. It waits to be listened to.